the standard cultural memory of the Apollo program is one of inevitable destiny. We look back at the grainy black and white footage of Neil Armstrong descending the ladder and assume that the path to that moment was clear, linear, and assured. We imagine that when President John F. Kennedy stood before Congress in May 1961 and committed the nation to landing a man on the moon, he did so on the advice of engineers who had a blueprint ready in their back pockets. The reality, as distilled from the historical record, is terrifyingly different. This is Distilled. When Kennedy announced the goal, the United States did not possess a rocket capable of lifting a lunar payload. It did not have a computer small enough to navigate a spacecraft. Computers of the era were the size of ballrooms, and the concept of a portable guidance system was science fiction. The agency did not know if the lunar surface was solid rock or a deep ocean of electrostatic dust that would swallow a lander whole. Most damning of all is the timeline of experience. On the day of the announcement, the total duration of American spaceflight experience was 15 minutes. Alan Shepard had flown one suborbital hop. He had not even orbited the Earth. He had simply been shot up and fallen back down. In contrast, the Soviet Union had already orbited animals and a human being. The giant leap was not a calculated engineering project. It was a political gamble made with almost zero technical collateral. The objective of this episode is to move beyond the right stuff narrative, the story of brave men in silver suits, and focus on the distilled essence, the management, the software, and the industrial mobilization. We are distilling One Giant Leap by Charles Fishman, a text that argues the moon landing was not just an adventure, but the singular event that catalyzed the modern digital world. We will cross-reference Fishman's journalistic account with the hard science of the Apollo guidance computer's source code, specifically the Luminary 099 build. Recent 2024 to 2025 studies on lunar dust toxicity and the forgotten memos of the managers who actually ran the program. The promise to the listener is simple. You think you know the story of the moon landing, but you only know the story of the astronauts. This is the story of the 400,000 people who built the ladder they climbed. The Impossible Management Challenge. The central thesis of Fishman's One Giant Leap is that the primary invention of the Apollo program was not the Saturn V rocket, but the management structure required to build it. The scale of the undertaking is difficult to visualize in modern terms. It was the largest non-military mobilization of resources in human history. The project consumed more than just money. It consumed time on a metaphysical scale. It is estimated that the Apollo program required approximately 1 million hours of human labor for every single hour a spacecraft spent in flight. This ratio of preparation to execution is unprecedented. The program involved 20,000 distinct industrial firms and universities, employing a workforce that peaked at nearly 400,000 people. The challenge was not merely logistical, it was one of precision integration. NASA had to ensure that a bolt manufactured in Ohio would fit perfectly into a nut manufactured in California, with zero margin for error, despite the parts never meeting until final assembly at Cape Canaveral. To achieve this, NASA essentially had to invent modern systems engineering and configuration management. They created a tier system of contractors, with prime contractors like North American Aviation and Grumman overseeing vast pyramids of subcontractors. Fishman illustrates this through the lens of the fourth branch of government. For a brief decade, NASA operated with such budgetary and industrial influence that it dictated the direction of American education, materials science, and manufacturing standards. The book argues that the management technology, the ability to coordinate massive, multidisciplinary teams toward a singular, clearly defined deadline, is a legacy as enduring as the physical hardware left on the lunar surface. The Digital Revolution Catalyst. Perhaps the most surprising insight in One Giant Leap is the direct causal link between the Apollo program and the smartphone in your pocket. In the early 1960s, the integrated circuit, the microchip, was a novel, unproven technology. It had been invented only a few years prior by engineers at Fairchild Semiconductor and Texas Instruments. The prevailing wisdom in the military and industrial sectors was that vacuum tubes were reliable, transistors were promising, but microchips were flimsy, expensive toys. NASA faced a physics problem that forced their hand. A computer built with vacuum tubes would be the size of a building. A computer built with discrete transistors would be the size of a refrigerator. The lunar module and command module had strict weight limits. The guidance computer needed to fit into a small bay and weigh roughly 70 pounds. The only technology that could theoretically achieve this density was the integrated circuit. NASA made a bet that changed the world. They decided to build the Apollo guidance computer using ICS. But they didn't just buy them, they bought the market. In the early years of the program, NASA purchased approximately 60% of the total United States production of integrated circuits. This massive injection of capital did two things. Reliability. NASA demanded man-rated reliability. They forced manufacturers to perfect their production lines, creating rigorous testing protocols that eliminated defects. The chips had to be safer than a parachute. By scaling up production to meet NASA's demand, the price of the microchip plummeted. In the span of a few years, the cost of a single chip dropped from roughly $1,000 to $15. Fishman argues that without Apollo acting as the first customer and underwriting the R&D risk, the digital revolution would have been delayed by a decade or more. Silicon Valley exists in its current form because NASA needed a computer to go to the moon. The LOL memory and the human hand. While the narrative of Apollo is often one of high technology, one giant leap reveals a surprising reliance on manual craftsmanship. The most striking example is the memory of the Apollo guidance computer. The software that flew the missions, the actual code written by Margaret Hamilton's team at MIT, could not be stored on magnetic tape, too heavy, too fragile, or standard read-write memory, susceptible to radiation and power loss. It had to be hardwired into the machine. The solution was core rope memory. This memory consisted of woven copper wires and magnetic ferrite cores. The programming was physical. If a wire passed through a core, it represented a binary 1. If it passed around the core, it represented a binary 0. This meant that the software had to be physically woven. The weaving was done by workers at Raytheon, many of whom were women recruited from the textile industry. They were affectionately nicknamed the Little Old Ladies, LOLs, and the memory became known as LOL memory. These women sat at looms, threading copper wire through tiny metal donuts with needles, following a pattern dictating the flight path of the spacecraft. A single error, a wire going through instead of around, could result in a navigation failure in deep space. The juxtaposition of the space age and the Stone Age, weaving, is a defining image. The forgotten workers and moon dust. Fishman shifts the focus from the astronauts to the engineers and laborers. He details the story of the spacesuit, which was not built by a defense contractor, but by the International Latex Corporation, Playtex, a bra manufacturer. The hard engineers at Hamilton Standard, who made propellers, struggled to build a flexible joint for the suit. The soft goods experts at Playtex knew how to make fabric move with the human body. The resulting suit was a masterpiece of 21 layers of neoprene, nylon, and Teflon, all sewn by hand. The seamstresses who stitched these suits worked with an intensity born of the knowledge that a variance of 1/32 of an inch in a seam could cause a rupture in a vacuum. The book also touches on the sensory experience of the moon, specifically the smell. Fishman recounts the anecdotes of astronauts who, upon returning to the lunar module and removing their helmets, smelled a distinct odor clinging to the dust on their suits. They described it as spent gunpowder or wet ashes. This sensory detail serves as a bridge between the sterile vacuum of space and the human experience of exploration. The deep dive. In this section, we pivot from Fishman's narrative to a rigorous technical fact-check, utilizing the provided research snippets to add nuance and verify claims. We examine the Apollo guidance computer's software architecture, the toxicology of lunar dust, and the sonic branding of the mission. The 1202 alarm, a triumph, not a glitch. Popular culture, most notably the film Apollo 13 and the dramatic tension in First Man, often depicts the computer alarms during the Apollo 11 descent as a terrifying malfunction that nearly aborted the mission. The research suggests a different interpretation. The alarms were evidence of a resilient system functioning exactly as designed to save the crew. The 1202 alarm and its cousin, the 1201, was generated by the Apollo guidance computer during the final descent to the lunar surface. The code 1202 translates to executive overflow, no vac areas, while 1201 means executive overflow, no core sets. The root cause was a hardware configuration error, not a software bug. The rendezvous radar switch had been placed in the slew position, likely following a checklist that hadn't been updated to reflect new procedures. In this mode, the radar's power supply was out of phase with the computer's reference signal. This caused the radar to send a flood of spurious interrupt signals to the computer, specifically 6,400 interrupts per second. Each interrupt forced the computer to pause its current task and check the radar data. The Apollo Guidance Computer Operating System, designed by Hal Laning and built by the MIT Instrumentation Lab, utilized a priority scheduling architecture. It organized tasks into jobs with assigned priorities. High priority, guidance equations, engine throttle control, attitude maintenance. Low priority, updating the astronaut's display, processing radar data that wasn't currently needed. When the radar interrupts flooded the CPU, the computer realized it was running out of time to complete its processing cycle, 2 seconds. It effectively said, "I am overloaded." Crucially, instead of crashing, the modern blue screen of death, the software triggered a bailout routine. This routine terminated all low-priority jobs, cleared the processing queue, restarted the high-priority jobs immediately. This restart happened almost instantaneously. The pilot, Armstrong, saw the alarm and a brief blanking of the display, but the engine control and guidance navigation never stopped. The software sacrificed the nice-to-have, display updates, to preserve the need-to-have, flying the ship. In mission control, the decision to continue landing, go, despite the alarm was made by Steve Bales, guidance officer, relying on the expertise of Jack Garman. Garman had a handwritten cheat sheet of alarm codes under the glass on his console. He knew that 1202 meant, "I'm busy, but I'm working." He advised Bales, "We're go on that alarm," provided it didn't become continuous. The 1202 alarm was not a failure. It was a successful demonstration of graceful degradation. The system protected the mission from a hardware error that would have frozen a less robust computer. Lunar Dust, the Toxicology Update, 2025. Fishman's book mentions the gunpowder smell and the early fears that moon dust might be explosive or chemically toxic. We can update this narrative with recent scientific literature found in the research snippets, specifically studies from 2023 to 2025. The smell of the moon is real. Astronauts consistently reported it upon repressurization. The leading scientific theory is dangling bonds. On Earth, dust particles are quickly passivated by oxygen and moisture. Their chemical bonds are satisfied. On the Moon, the dust is constantly smashed by meteorites and solar wind in a vacuum, leaving open reactive chemical bonds on the surface of the particles. When this activated dust hits the moist, oxygen-rich atmosphere of the lunar module, it instantly oxidizes. This rapid chemical reaction is perceived by the olfactory system as a burning smell, gunpowder or ozone. Early in the program, NASA feared the dust might be pyrophoric, spontaneously combusting, or acutely toxic. The 2025 UTS study, a recent study published in Life Sciences in Space Research, June 2025, provides a nuanced update. Researchers exposed human lung cells to lunar dust simulants and compared the reaction to Earth-based urban particulate matter, pollution. Surprisingly, the study found that lunar dust was less toxic than city pollution in terms of chemical stress. It did not cause the severe oxidative damage seen with terrestrial pollutants. While chemically less active in the lungs, perhaps due to rapid passivation, the dust remains a severe mechanical hazard. The particles are jagged shards of glass, obsidian-like, that do not erode. A 2023 study indicated that high-dose inhalation leads to persistent inflammation and immune dysregulation, not because of poison, but because the physical particles shred cellular structures. The dust won't poison you instantly like cyanide, but breathing it chronically on a lunar base would be like breathing ground glass, leading to silicosis-like conditions. The positive spin is that it is manageable with filtration, unlike the biological or chemical toxicity originally feared. Sonic identity, the Quindar tones. To satisfy the audio branding inquiry, we analyzed the iconic beep-beep heard in Apollo communications. These sounds, known as Quindar tones, are a perfect example of analog ingenuity solving a distance problem. The Apollo spacecraft communicated with Mission Control, Houston, via the Manned Spaceflight Network, a series of tracking stations around the globe. Houston was connected to these remote stations by dedicated telephone lines. To activate the massive radio transmitters at a remote station, e.g. in Australia, Houston needed a signal. They couldn't run a separate control wire halfway around the world. They used in-band signaling. They sent a specific audible tone down the same telephone line as the voice. Intro tone, 2525 Hz, a pure sine wave lasting 250 milliseconds. When the Capcom capsule communicator in Houston pressed the push-to-talk button, this tone was generated. The equipment at the remote station heard this specific pitch and instantly turned on the transmitter. Outro tone, 2475 Hz, a slightly lower sine wave. When the Capcom released the button, this tone signaled the transmitter to turn off. Many assume the astronauts generated these beeps. In reality, the astronauts never heard them, or heard them only faintly. The beeps were generated on Earth for Earth equipment. We hear them on the archival recordings because the recorders were tapping into the main line. These tones have become the sonic shorthand for spaceflight in popular culture, used by bands like Quindar and in countless films to evoke the feeling of distance and technology. The Distilled, actionable advice. This section translates the historical and technical lessons of Apollo into actionable advice for the modern listener. We distill the wisdom of Gene Kranz, Bill Tyndall, and the Tiger teams into 3 concrete takeaways. 1. Work the problem. Crisis management. This mantra is famously attributed to flight director Gene Kranz, particularly during the Apollo 13 crisis. When an oxygen tank exploded, the initial reaction in Mission Control was confusion and denial. The telemetry didn't make sense. The human instinct in such a moment is to panic or to guess at a solution to relieve the tension. Kranz's directive was specific. Let's work the problem, people. Let's not make things worse by guessing. This approach strips away emotion. It forces the team to rely only on verified data. It rejects the quick fix in favor of the correct fix. In a modern business crisis, a server outage, a PR scandal, a product failure, apply the Kranz protocol. Stop the guessing, silence the speculation in the Slack channel. Verify the state, what do we know is true, not what we hope or fear. Sequence the actions. Do not try to solve the whole crisis at once. Solve the immediate stability problem. Then the next problem, then the next. As the character Mark Watney says in The Martian, an heir to this philosophy, if you solve enough problems, you get to come home. 2. The Tiger Team approach. The term Tiger Team was popularized by NASA and the military to describe a specialized cross-functional group deployed to solve a specific high-stakes problem. The Apollo 13 Black Team is the archetype, a group of experts locked in a room to figure out how to build a carbon dioxide filter out of a sock and a manual. A Tiger Team is different from a regular committee. It is composed of undomesticated specialists, the absolute best experts, regardless of their rank or department. They are removed from business as usual. They do not attend regular staff meetings. They have one goal: They have the authority to bypass bureaucracy to get the answer. If your organization is stuck on a critical issue, do not form a working group. Form a tiger team. Pick the best. Pull your best engineer, your best designer, and your best operator. Isolate them. Give them a war room, physical or digital. Clear their calendars. Define done. Give them a single binary goal, for example, fix the latency issue. Once the problem is solved, the team dissolves. This prevents scope creep and keeps the energy high. 3. The Tyndallgram, communication style. Bill Tyndall was the chief of Apollo Data Priority Coordination. He was responsible for the mission techniques, the choreography of the landing. He found that the sheer volume of bureaucratic paperwork was drowning the engineering decisions. People were being too polite, too vague, or too slow. Tyndall began writing internal memos that became known as Tyndallgrams. They were legendary for their tone, blunt, conversational, funny, and relentlessly focused on the truth. He used humor and plain English to cut through the engineer speak. He didn't care about hierarchy, he cared about the physics. Adopt the Tyndallgram style for high-stakes communication. Drop the jargon. If something is broken, say it is broken. Don't call it a suboptimal outcome. Be human. Use your natural voice. Humor, when appropriate, disarms defensiveness and builds camaraderie. Focus on the data. Be blunt about the problem, but constructive about the solution. A culture of technical truth, where bad news travels as fast as good news, is essential for safety and innovation. To distill it all down, the moon landing was not a miracle of destiny, it was a miracle of management. It was achieved by 400,000 people who built a ladder to the stars out of copper wires, hand-sewn fabric, and blunt memos. It was the ultimate triumph of the Tiger team and the work-the-problem philosophy. As we look toward the next giant leap, to Mars, the lessons of Apollo remain the blueprint. We don't need to be perfect, we just need to be resilient enough to handle the 1202 alarms when they inevitably flash. If you want to read the actual assembly code that saved Apollo 11, yes, it's on GitHub, or the 2025 study on lunar dust toxicity, check the research notes, link in the pinned comment. If you enjoyed this distillation, subscribe, hit the bell icon, and look forward to our next episode of Distilled.